This is an online lecture that covers some of the modern techniques of mineralogical analysis. Today we focus on the use of lasers and X-rays to understand mineral compositions. Recall from earlier lectures that the electromagnetic spectrum is a continuum of energies that speaks to the propagation of what we call light, but that includes things from radio waves at the longest wavelengths to gamma rays at the shortest wavelengths. Somewhat in the middle is visible light, the part of light that we're most familiar. Can we use light to tell us something about the composition of minerals? And recalling that all light is the product of electrons moving from higher to lower energies, can we use that information to understand the composition of the minerals that we know and love? Recall, too, that when you heat hydrogen to the point where it'll emit light and send that light through a prism, you discover there are 4 frequencies being emitted. And those 4 frequencies, of course, are 4 individual wavelengths, or colors. They are 1 red, 1 green, and 2 violet. There's also infrared and ultraviolet emissions, but we can't see those with the naked eye. However, if we had detectors that were tuned to those frequencies, we'd certainly be able to see them. Think of this backwards. If you had a hot gas in a tube and you saw these 4 colors, you would know that it was hydrogen. This is the characteristic radiation from hydrogen. Also, please recall that these 4 colors, the characteristic emissions from hydrogen, are a consequence of the electrons moving from a higher energy orbital position to a lower one. This emits light, 1 photon for every jump, and the energy of this light can calculate the energy of the photon that is emitted. Recall, too, from lab that if we subject certain minerals to ultraviolet radiation, we can induce this characteristic emission from certain elements. This is the phenomenon known as fluorescence, the induced light from excitation. Certainly, these minerals in this picture are responding to short wavelength UV by showing a variety of colors that are dependent on the elements that are trapped in the minerals. In most cases, these are minor amounts of elements, but in some cases, they are the major building components of the mineral. Elements heavier than hydrogen, of course, have more than 1 electron in each orbital and house more electrons. The number of jumps becomes a little more complicated as the energy levels are shifted to adapt to the spin states. However, the rules are still the same. We will receive characteristic radiation, predictable energies, when electrons move from higher energy states to lower ones. Therefore, each element has a fingerprint, if you will, an emission spectra or fluorescence spectra that identifies it based on its electron structure and the way those electrons move from one energy to another. Our friend hydrogen's emission spectrum is on the top. Mercury is below it. Few more complications because of the electrons that are involved. Neon, yes, the neon that's found in a neon light, emits the spectrum on the bottom. If you were to take a prism to the light being emitted by a neon lamp, this is what you would see. You can also think of this in terms of absorption as well, for these elements will absorb the energies needed to move the electrons around as well. And on the bottom, I have an example of absorption spectra. Notice the black lines that are now missing from white light for hydrogen. In order to see emission spectra, the material has to be pretty hot. It has to be excited so the electrons jump back down to their lower energy positions. There's a couple of ways we can do this. On this slide, we see 2 popular ways of ionization, or heating up the materials, so that we can characterize emission spectra. One of them is inductively coupled plasma. This uses an argon gas and a current to induce the electron jumps necessary and completely ionize the particles involved. The second one is X-rays. We can use X-rays to induce ionization in samples because X-rays are high energy. We do this by putting a metal under a high current in a vacuum, and then it produces X-rays in much the same way a light bulb filament produces light. I want to use the generation of X-rays to underscore what's happening in generating characteristic radiation in a couple of fronts. One, it's important to realize that when we heat the materials in an X-ray tube, they can generate characteristic X-ray radiation, and that's what we would use for our X-ray beam. But in all cases, the generation of emissions or fluorescent is contingent on meeting certain energy requirements to make electron jumps happen. You can get a material hot, or in this case, put it under a high electrical potential, but that doesn't mean you're going to get characteristic radiation. What you will get is a background of collisions that happen of electrons losing energy into other electrons. In X-ray radiation, this is known as white radiation. But it's true for any kind of radiation that we look at. If you want to reach characteristic radiation in a material like copper, as shown on this slide, you have to increase the electrical potential to 25 kilovolts before you start seeing the peaks. Above that, you will continue to see characteristic radiation. Again, I'm using this as an example because it is this characteristic radiation, X-rays, that can then be used to ionize other samples so that we know their characteristic radiation. What I've been describing to this point is the bulk ionization that happens when you subject all of the sample to ionizing energies. What if you're just interested in a small volume? Well, we have techniques for that as well. Two principal techniques is the use of particle beams. Shown here on the left, the particle involved is focusing electrons, an easy process that we've been doing since the mid-20th century. It involves generating the electrons at a high potential and then focusing them, much like a light beam, into a narrow beam using magnets. On the right, we have laser sampling. Lasers, of course, are monochromatic light sources that appear in a near-focused beam. We're able to take that near-focused beam and concentrate it on a single point. With high enough energies, these can heat and liberate atoms from a sample, as shown in the cartoon. As you might imagine, these techniques are useful for analyzing individual spots on mineral grains. Let's begin with the microionization technique, which yields visible and near-visible spectra. Laser-induced breakdown spectroscopy is a technique that applies a laser to a sample, heats the sample, and produces a light that is then characterized by a spectrometer. MSU Texas houses an ESI New Wave Ocean Optics Libs Elite. This uses a yttrium garnet UV laser that is then applied to a sample from sizes ranging to 50 to 200 microns. Recall that a human hair is 70 microns, so we're on the same scale. The spectrometer can read light from 198 to 960 nanometers, meaning that it covers the near UV, visible, and near visible infrared ranges. It accepts quite easily anything that fits into a 1 to 2 inch round sample format. The nice thing about libs is you can work down on the hair width scale with virtually little to no preparation. You can stick a sample in there and shoot it if you know what you're doing. It works at atmospheric conditions, so there's no waiting for a vacuum pump to kick in and take the air out of the way. The trade-off is it's pretty low accuracy and it's difficult to quantify. Here's how the technique works. The laser is applied to the surface gets very hot. It starts to volatilize and make a small cloud above the sample. This emits light as a plasma as the electrons come crashing back down to the ground state. That light emission is then sent to a spectrometer, and you're left with a tiny crater, like those seen in the gypsum crystals above. This is not terribly destructive. The holes are 70 microns across, but nonetheless it is a destructive process. At the heart of the LIBS is laser ablation. That is, exciting a small amount of the sample using a high-powered laser. That has its own problems, because the laser actually has to interact with the mineral lattice. We've found through testing that there are several parameters that help to produce clean, good-looking analyses time and time again. However, we continually find that we need to make adaptations depending on individual mineral specimens. In all of the techniques we're discussing today, we are measuring energies or wavelengths through spectrometry. And what we're interested in is the high-intensity radiations that are produced over limited ranges of wavelengths or energies. These are peaks. But part and parcel to the technique is radiation that's being caused in between the peaks. This excessive radiation is known as background, and it is impossible to avoid. In fact, it's one way to know that your spectrometer is working, because a zero value tells you something is terribly wrong. Background radiation is everywhere and has several sources depending on the instrumentation. In the LIBS, we have 7 separate spectrometer units, and each produces its own background values. Most of this is electronic noise. On the top graph on the left, you can see what the raw data looks like. There are certainly some peaks, but the lower levels range from 25 to about 200 counts. These are all background values. So one of the first steps to do in many spectrometry techniques is to subtract that out numerically. The bottom graph shows a background subtracted profile, and now we can just focus on the peaks. One of the hazards of LIBS is that each sample behaves slightly differently under the laser. A way to get around this is to normalize the intensity of the peaks to something that doesn't change from material to material. Well, that really isn't the material itself, but the atmosphere in which it's being shot. Recall that our atmosphere is mostly nitrogen, so if we look for the nitrogen characteristic peaks and see how their intensity changes from each given shot, we can then use that to constrain the rest of the intensities. The characteristic nitrogen peaks are shown in the upper right corner. The gypsum that was shot and produced the spectra to the lower left has been normalized to the nitrogen values. This can then be compared to other materials. On this slide, we see how the LIBS technique has been applied to a series of amphibole grains in individual granites from the Wichita Mountains of southwestern Oklahoma. There are some gross similarities between each of the grains within each of the rocks. However, there are some differences, mostly in intensities of the sodium 589 peak and the potassium 769.9 peak. Seeing these differences can be somewhat challenging, so the LIBS technique has its limitations in that we know what elements are there, but it can be difficult to say how much of each is present. The instrument is most useful for discriminating differences and pointing out and highlighting those differences.